So in our yesterday's session, we have seen regarding character drivers. We have completed like open, read, write, lseek, release. Today we'll be looking into ioctl. So ioctl, it stands for input and output control. We know that device files in Linux, they represent physical devices. Each and every device driver, they give us a device file. So, and we know we have write and read system calls for writing and reading from the device file. But these write and read system calls are not sufficient. There may be some specific operations of a device which cannot be possible using read and write system call. Example, in case of a CD drive, ejecting the media. So if you want to eject the CD drive, it cannot be possible using read and write system call. Changing the baud rate of a serial port, adjusting the volume, or reading or writing device registers. This all operations cannot be performed using a read and write functionality of the device driver. So in this case, for these scenarios, they have added ioctl. So ioctl is provided for device specific custom commands, the commands which are custom to the device. So example can be format, reset, and shutdown. These commands which cannot be provided by standard system calls like read and write, we can provide it using ioctl. So the ioctl, this is the system call and this is the declaration of ioctl. The first argument is file descriptor. The second argument is a request, and this request is either format or reset or shutdown. Depending on the request, you will be having the third parameter. Some request may not require a third parameter, some may require a parameter for that. So each device can have its own ioctl command, like which can be read ioctls, write ioctls, both. Read ioctls means the information is sent from the process to the kernel. Write ioctl is from the kernel to the process. So there are already many known ioctl calls. If you go to man page, section 2, ioctl list, you will find out list of ioctl calls which are present in Linux. So this is from like kernel version 1.3.27. Like this is not fully complete. This is a very incomplete list, but you can find out what all ioctl commands are there. So these are the ioctl request number. This is just a hash defined to this. Hash defined on this to this is present in this header file. So if you're using a number, then there is no need of including this header file. But if you want to use this, then you have to include the header file. So you can see a lot of CD-ROM, pause, resume. Void means it does not accept any argument. So eject is one more, CD-ROM eject, volume control. So these are the ioctl commands. And you can see for file descriptors you have one like block get size. If you want to get the size of your block device, you can send this ioctl command. So ioctl, open the file descriptor, block device file descriptor, and send block get size, and the return value is unsigned long. So you have to pass a pointer to an unsigned long. So let's see like what we can do here. So block size. So if you want to find out the size of a block device, I can use ioctl request block get size. The return value is device size as a number of 512 byte blocks. So it will give us a blocks. It will not give us in a size. And each block is of 512 byte size. So let's try this. So my hard disk is dev SDA1. So if you go to the SDA1, is a block device. So SDA1 is a block device. I want to find out the blocks, number of, what is the size of this device. So I open the device in read-only mode, and I know the block size, get size. The value of the request will be 1260. This is from the man ioctl list. So from the man ioctl list, I know block get size is 1260. Okay, so no header of including any header file. So I just pass 10 to 1260, and it needs unsigned long pointer. So I'm using passing address of this num blocks. So I print the return value, the number of blocks, and I know that number of blocks, each block is of size 512 bytes. So each block is of size like 512 bytes. So I divide it like this much to get in GBs. So for KB, MB, and GB, we have to divide it with this number. So then I will know the size of my disk is in GB. So let's run this block size. So it needs permission to open the device SDA1, and you can see SDA1 is having read-write permissions only to the root owner and the disk group, and I am not in the disk group. So I'm not in the disk group, so I need to use either root user or I have to add myself into the disk group. So let's run sudo block size, and you can see this many blocks are present. Each block is of like 512 bytes. If I divide it for GB, I get like 99 GB. This is my hard disk size. I can verify it with df-h command. So you can see dev sda1 is like almost 98 GB. So it's 99 GB. So this is what is, we have used ioctl to find out like the disk size or the number of blocks present on your block device. So there is one more way, like if so there is one more, like block a great size, it returns unsigned long. If my hard disk size is more than 2 TB, if my block device size is more than 2 TB, this will fail because we cannot store more than 2 TB here. So for this reason, they have added a new ioctl like block get size 64. This will directly give us 64-bit result, which is a size in bytes. It will now directly give us the size in bytes. This is giving the size in sectors, and each sector is in blocks. Each block is like 512 bytes. And I can now directly call, I use a 64-bit, I pass the address, I set the request as block get size 64, I divide it like by this many times to get in GBs. So I run this again, so I get my directly in size. So we have seen an example from a user space, the use case of ioctl. ioctl is used to perform device specific operations, custom commands which can only be provided by that particular device. So how can I implement it in my character device driver? So the ioctl method, the character driver is unlocked ioctl. So previously we used to have ioctl, but now we have unlocked underscore ioctl, and it have like 3 parameters: file pointer, the command which you are sending from the user space. We have sent like block get size. This is what is the command, and the argument if you're passing an argument. So this is optional. Like if you want, you can pass. Depends on whether the command needs an argument or not. So let's implement it in our character driver. So I have added unlocked ioctl, and I'm saying it device ioctl. So this is my function which will be executed when I call ioctl from my user space. What I'm doing here is I'm printing the value of command. I'm printing the value of arg. So from the user app, I'm just opening the device node. I'm calling ioctl. I'm passing the command as 1 and the argument as 10. In the second case, I'm not passing any argument. I'm only passing the command as 1. Let's see what will be the values which will be received by our device driver. So what I have done is like as I was always running ins mod and rm mod, I have added an alias in my bash rc file. So alias mod, which will just remove current existing module and insert the hello.q. So this is just to speed up. So I run mod, it will remove and it will insert. So it should have like, so as module was not existed, it failed. So let's insert it again. We have to compile it before. There was no KO there. So I did make, and I can just say mod now. And I can say hello, it should be present. So hello is added now. So from my user app, I'm just calling ioctl twice. One with an passing an argument, other without argument. Let's do a dmessage minus c. And let's add it in my screen. Let's run this screen. So I have to give permissions. So you can see first I have passed 1 as a command, an argument as 10, and we have received the same. In the next case, I have only passed command, but reading the argument value, I'm getting garbage, some garbage value here. So we have seen how the values are being received by the ioctl in the device driver code. So what most ioctl implementation, they basically consist of a switch statement, which will select the behavior according to the command argument. So almost all the ioctl implementation, they have a switch statement, and the switch statement will change the behavior depending on what you pass as a command value. So I have a switch statement and I have now cases for each and everything. So for 0, 1, what I will do is I want to send the length of the buffer. So this is the previous code which we are working with from past 2-3 sessions. So I want to send for 0, 1, if someone sends me a 0, 1, I will send the size in the argument field. So I'll send the size in the argument field and he should send me an integer unsigned. If someone says command 02 without any arguments, I will just clear the buffer. So I'll set all the buffer contents to 0. If someone sends me a 03 as a command value, I will fill the whole buffer with a particular character. Like the character will be passed by the user. So I read the character, calling get underscore user, and I call memset kernel buffer, and I set that particular character. So I set the whole buffer with this particular character. So almost all the ioctl implementations will have a switch case, and the behavior will change whatever. You will be having different cases for each and every command. So here we have 3 cases, as it is a buffer device, as it is a virtual device. We have like for length of the buffer, clear buffer, and fill character. So from the user app, first I open the device, MSG, and I call 01, send the command as 01, and I now get the length, pass an unsigned pointer, and the module will fill the length in this particular case. So I have the length here. Now I want to set the character as a I want to fill the whole buffer as with 8. So I send the command as 3 and set the value as 3. Then I change my offset back to 0 because this offset will be changed. So, and I read like 1024 bytes from the buffer, and I null terminate it and I print the buffer. So you can see, first I have sent a command 1 and it gave me the length of the buffer, which is 1024. Then I said fill character A and sending a command 3 and it was successful there. And then I said else, then I have read the buffer and we got all A's. So knowing this number is like not, we have to remember these numbers. It's not easy. So we can give a symbolic names. Symbolic names can be given to this numeric values to simplify coding. So basically what you will be doing is you will have a header file where you will give hash defines to each and every numeric values of the commands. And the user space program must also include this header file. So this header file which you make should be included in both the kernel module as well as in the user module. So this is the header file. We know 01 is for length of the module, 02 is for clear the buffer, and 03 is for like fill the buffer. So we have like created a header file with an hash defines, and I can change the code. So instead of having 01, 02, 03, I write the macros, and I have to include this header file in the user space. I can perform the same. I include the header file, and instead of calling 01, I just say get length fill buffer. This will make the code simpler and easier to understand. So there's nothing more here. So I load the module and I perform the same functionality. So we just what we did is we have created a header file and we shared it between the both kernel module and the user space app. So this is required as a kernel. There is no documentation for your device specific custom commands. Only your header file, which contains the commands numbers, should be provided to the user space for them to know what all commands are being present in the ioctl. So you have any doubts still here? So defining ioctl commands. So the first step when you're implementing ioctl in your device driver is you have to know what all commands you need to implement. Depending on your device, you have to identify what all commands I need to expose to the user space. So what normally programmer does is they start from either 0 or 1 and they go up from there. But using this is not a good idea. It's a very bad idea using numbers 0 or 1 and start 2, 3, 4 and all. Because the problem is 2 or more device nodes can have the same major number and they have the same ioctl command numbers. An application can open these device nodes and if they mix up the file descriptors, they can send the right command to the wrong device. And as it is working on the kernel, it can damage the hardware also. So the problem is with using a numbers 0, 1, 2, 3 is application can mismatch device nodes and can send wrong commands, ioctl commands to the wrong device and can damage the hardware. Like example is like I'm trying to change the baud rate of a non-serial device. I can change the baud rate of only a serial device. But if I'm trying to change the baud rate of a non-serial device by sending an ioctl command, it can have catastrophic effect. So it's better not use numbers. We have to create unique ioctl commands. To help create unique ioctl commands, Kernel provides us macros. This ioctl code is divided into 4 parts. To create a unique ioctl command, the ioctl code is divided into 4 parts. And the problem with this approach, where you have the header file, is you don't know what to pass. If someone gives you this header file and says use this header file to access my driver, perform ioctl, you don't know what to pass in the argument field. Here get length, should I pass a character? Should I pass an integer? Should I pass anything or not? So this is not clear from this header file. To make it clear, kernel has made macros and divided the ioctl code into 4 parts. Those 4 parts are type, number, direction, and size. Type is also known as magic number. So this ioctl code is divided into 4 parts, and the first part is type, which is 8-bit. So 1 byte is given to type. So type is 8-bit, 1 byte. You have to choose a type and you have to use it across your driver. So there are already some drivers using the magic numbers or types. You have to go to the Linux documentation. In the documentation folder, there is an ioctl folder. There you have ioctl number. So this first field code is the type or magic number. So these are already being used. 00, 02, 04, 06, 09. So these are already being used, and this is the sequence number. So this all first column is already being used by different drivers. So it's better not to use whatever is present in this particular document. The magic number or the number should be unique and should not be used by any other module which is mentioned here. So first step is you have to go to this document and verify if anyone is using this, whatever your magic number you have thought is being used by some other module. So once that is done, you have completed the first part. Then is the number. This number is 8 bits wide. It's a sequential number. So like we have 0, 1, 0, 2, 0, 3. This is the same number. Then we have direction. Whether I want to pass any parameter, in this case I have to say no direction. Whether I want to read from the device, whether I want to write to the device, whether I want to read or write to the device. So this is the direction. Now I can understand using the direction whether I want to read, whether I want to write or read-write. Size of the user data. So this single command, 32-bit command, is divided into 4 parts: type, number, direction, and size. And this size depends, like it can be either 13 or 14 bits. It depends on the architecture. If you want to find out what is your size, you can use this size bits. So the header file for this is linux ioctl.h. We will be having this all in this particular header file. So this header file, it defines macros to generate a command number. So we were generating a command number just by 0, 1, 0, 2, 0, 3. Now using these macros, we have to generate our command number. So if you have a command which do not accept any argument, you have to use this macro _io. Type is your magic number. This is your sequential number. If you have a command which is reading data from the driver, then you have to use ior, and I have to specify what I am reading from there. If I am writing, I have to use iowr. If I am doing bidirectional data transfer. So you can see here we are passing type, number, and data type. We are not passing direction and size. So direction and size are derived from the macros. So size is derived from the data type. Direction is derived which macro you are using. So I have included linux ioctl.h, and I'm generating command numbers which I can pass as a second argument to the ioctl. So I have set some magic numbers, like this is first magic number, this is my second magic number. So _io is when I am not expecting any data transfer. So I set first argument as a magic number. This is my sequential command. So I'm checking if I change the magic number, will the value of the command change? In the second case, I'm changing the command number, sequential command number. I'm checking again, if I change the command number, keeping the same magic number, what will be the value of command? In the third case, I'm trying to read from the 5 word, and I want to read integer. So I have to say int. I'm just changing again the sequential number. In this case, I'm performing read and write, and I'm reading both int and writing int from the device driver. So you can see these are the command numbers given by the macros. Once you fill the macro, it will give you a command number, which is unique for your driver. So you can see IOC magic number 1 and 1. Then I just change the sequential number, command number, and I got 602, 6901, 6902. I have used a different macro, I get a big number. It's not a sequential if I'm using a different macro. Just changing the command number, this is incremented. If I'm using WR, you can see a different number is being generated. So any queries still here? So if I have a command number and I want to find out the magic number or the sequential number or size or direction, I have again macros. These are the macros which will decode information from the command. Previously, we generated a command number from the macros. If I want to decode the information from the command number, I can use these macros. Underscore IOC type, if you give a command number, it will give you the magic number. Underscore IOC NR, it will give me the sequential number. Underscore size will give me the size. Direction will give me either it is none, read, write, read, write. So I already have commands like this were the commands which I have a magic number L. Then I have like 3 commands. One is not accepting any argument. This is performing write operation on the driver. This is performing read and write. So I have the command numbers. Now if I want to find out the magic number, I use, if I want to find out the sequential number, I use NR. If I want to find out the magic number, I use type. If I want to find out the size of the command, I use size. If I want to find out direction, I use dir. So these are decoding information from the command number. So you can see the sequential number. L in ASCII is 108. This is the 108. And I'm not passing any parameter, the size is 0. For int, I got size 4. And for char, I got 1. None. This was the direction which we have set. So now I update my code with this thing. So I have updated my header file. So I set the magic number as 21. Not 21, this is in hex. Then now I'm using those macros, IOR, IO, and IOW. And using these macros, now I easily understand like get length will read from the device driver, and I need to pass a pointer to an unsigned int. Clear buffer will perform clear operation, but I no need of passing any third parameter to ioctl. Fill buffer, I need to write a unsigned character to the driver. So using this IOR, IO, and IOW, I'm easily able to understand what I need to do. And I have set a max commands as 3. So now I have like command. So I have included this header file, ioctl command.h. The code is same here, only the macros has changed. Get length. The value of these commands have changed. The code is same. So you can see it worked perfectly. And you can see the command numbers here. Previously we were using 0, 1, 2, 3. Now we have like big numbers. And the code is the same. I'm passing length, I'm passing character. So using these macros now it is very easily understandable what is expected by the device driver. So in this case, there is no need of passing the kernel source code to the user space team. You can directly pass the header file and they can easily understand. So what should be the return value if someone pass an invalid command, like whatever is not present in those header file, if someone passes 0, 1, 2, 3, what should I return? What should I return? As per the POSIX standard, if someone passes an unknown ioctl command number, I should return enotty, which stands for inappropriate ioctl for the device. So if someone sends me a command number which is not being supported by my driver, I have to return enotty. So I have updated my code. So if someone sends me a command which I have not supported, so switch case will come to default. The default I am sending enotty. This is the as per the POSIX standard. From the user app, I'm trying to send 4. 4 is not supported by the command number 4 is not supported by my driver. So in this case, I have to get enotty. So you can see P error converted the enotty into string. Inappropriate ioctl for the device. So there is a macro known as access underscore OK. As we are passing user space pointers to ioctl, we have to be careful. So we can use copy from user and copy to user to safely copy data from user space to kernel space and vice versa. These functions are not efficient in case if I'm copying 1 byte, 2 byte, 4 byte, or 8 byte. I can use put user and get user. So these are safe functions like copy from user and copy to user, and put user and get user are safe functions. I can safely copy data from user space to kernel space and vice versa. I don't want to copy that data. I want to verify whether the user is passing the correct data or not. In this case, I can use a macro known as access underscore OK. If I want to verify the address without transferring data, I can use access underscore OK. So this access underscore OK takes 3 arguments: type, if I want to perform read operation or write operation. So this verify read is either you are reading the user space memory or writing it. So verify read means if you are reading a user space memory. Verify write means if you are writing on a user space memory. This is the user space address. Size will depend on the ioctl command. If I need to perform both read and write, I can directly use verify write as it is a superset of verify read. The return value of access OK is reverse. So it not returns 0 on success. It returns 1 for success and 0 for failure. And if access OK fails, you have to return E fault. So if access OK has returned 0, then you should return E fault. From Linux kernel 5.0, the first argument is being removed. So no need of passing type. It will perform checking of both read and write. And you only need to pass these 2 arguments. If you're using an older kernel before 5.0, you need to pass type. But if you have the latest kernel, you need to use only pass the first these 2 arguments. So I have the latest kernel here, 5 point more than 5. So No need of passing type there. So I get the size of the command using decoding macros, IOC underscore size. Now, what I'm checking here is I'm checking the magic number. If the magic number is not same, I'm saying it's not my TTY device. Since I'm returning E no TTY as per the POSIX standard. If the command sequential command is greater than the maximum commands I can support, in this also I'm returning E no TTY. Then I come and I check access OK. So access OK, I'm checking the argument and size. And access OK returns 1 on success, 0 on failure. So if has returned 0, mod of 0 is 1, and I'm returning default. So let's check this. In the user space code, I'm passing null. So what I have done is, so I have created one more ioctl command, get address, and this will give me, I have to pass long, and this will give me the address of the kernel buffer. So this get address will put the address of the kernel buffer into the user argument. So it is writing the kernel buffer into the user argument. What if I pass null here? Will the access OK fails or will it success? Let's try that. So access OK, it returned 1. So even if I have passed 0, access OK did not fail. Access OK returned 1 means it is successful. So what do you think when access OK will fail? Access OK can fail. It will, when it fails, it will return 0. Think of scenario where access underscore OK may fail. So access OK is checking the user space address. So if I have passed null, it failed. It accepted. So what can be a case where access underscore OK may fail? So let's find out. So I pass an unsigned long pointer and I store it in PTR. So the PTR is now pointing to a kernel address. Get address contains the kernel buffer address. The PTR is now pointing to the kernel address. What if I now send this kernel address to ioctl, to my driver? Let's see whether access OK works in this case. So in the first case, access OK return 1. This means it is successful. And I have the kernel address in my PTR. In the second case, ioctl failed with bad address. So ioctl default is bad address. So access OK returns 0. So access OK will fail if I pass a kernel address as an argument to ioctl. So access OK will only check whether the pointer you're passing is a user pointer or not. If you pass a kernel pointer, it will fail. So get address, it needs unsigned long. So get address, I have to pass unsigned long. What if I pass only a character? Will this work? Instead of passing unsigned long, I'm passing only a character. Do you think ioctl will fail? Let's look into our code. So here we are checking the size of the command. We are not checking the size of the argument. There is no way we can find out what is the size of the argument because it is a 64-bit. Whatever you're passing is coming here. There is no way if someone does not have a structure or something, if someone just send an int or char or point, I cannot find out what is the size of the argument. I can only find out what will be the size of the command. So there is no way I can find the size of the parameter. So whatever comes, I'm just writing 1, 2, 3, 4, 5, 6, 7, 8 into this argument. So what do you think will be the value of CH? Let's find out. So you can see this came A0. So I have to use this module. It gave me 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. It gave me the only 1 byte information. So ioctl was successful and it only gave me 1 byte. So you have to be careful, like whether you're passing the exact size or not. There is no failure here from ioctl. ioctl will be successful even if you don't pass the exact size. Till now, we were using 64-bit processes. If I say file on the user app, it's a 64-bit. How can I generate a 32-bit application using GCC on a 64-bit machine? I want to generate a 32-bit application using GCC. Can I generate a 32-bit application on a 64-bit machine?
Using the toolchain and target might help.
Target is the same, right? I'm generating for my host machine.
Yeah, but the architecture can change, I guess. Or toolchain windows.
So can I run a 32-bit on a 64-bit machine?
Yes, we can run.
Yes.
The way we do it in Windows 64, we can have exe for 32 and 64.
So we use like wow 64 on Windows. Here I can generate using GCC by passing M32. If I pass M32, the machine, M is for machine, M32 will generate me a 32-bit application. So you can see it has generated me a 32-bit if I pass this thing. Let's run this application. So this is the same code previously. I'm just calling get length and I'm trying to read the length from the length of the kernel buffer. So let's run this code. It's saying inappropriate ioctl per device. This is enotty, but everything is same. The kernel module is same. This is the same module, but it failed with enotty, and you can see there were no kernel driver device ioctl messages printed in the D message. So this means it's not even going to my driver. So how can I make this work? I want to use a 32-bit application. I have an old platform, but my driver is the latest. I want to use like 32-bit application, the old 32-bit application, which I have written like 10 years back. I want to use it for my latest machine. I don't want to port it to 64-bit. So yes, Linux support it. What you have to do is you have to add a new ioctl. Instead of unlocked ioctl, you have to use compat underscore ioctl, and you can see the arguments and the return values are all same. So if a 32-bit process calls ioctl on a 64-bit system, it comes to compat ioctl, and this compat ioctl should convert the data types. There may be data types which you are using are different in 32-bit and 64-bit. Like pointer in a 32-bit is different on a 64-bit. So in this function, you have to convert those compat ioctl. And one more thing, like if you want, you have to install the libraries if you want to compile it on a 32-bit on a 64-bit machine for 32-bit. You have to install apt-get install this thing, G++ multi. If you're compiling for 32-bit and 64-bit machine, otherwise it will throw errors. So if you're doing M32, please install this package. So in the code, I have kept unlocked ioctl. This is for 64-bit to 64-bit. Compat ioctl is when 32-bit calls in a 64-bit machine. So I'm saying use my device ioctl. As the arguments and everything are same, I'm saying use the same device ioctl. Either a 32-bit process calls it, or a 64-bit process calls it. So I'm calling get length, the same code. So let's run this. So if you want to know what mod is doing, I can just say set minus x. So mod is an alias. If I want to know what mod is doing, I say set minus x. It's a mod. You'll see it is running rm mod hello and ns mod on the hello. I can just disable it. So I run this user space app. When you do make, it will only generate 64-bit. So the 64-bit works, it gives me 1024. For compiling, I have to use GCC. Now I have 32-bit, and you can see my ioctl successfully executed. I got the length 1024 in case of a 32-bit application. So let's now see message get address. We have seen get length, unsigned int. So unsigned int in case of 32-bit is 4 bytes. What is the size of unsigned int in 64-bit? Will it change? Will the size of unsigned int changes in case of a 64-bit machine? So on a 64-bit machine, you have unsigned int as 4. So this is same in case of 64-bit machine. But this unsigned long, in case of 64-bit machine, it is light. And in case of 32-bit machine, it is 4. So what I'm doing in this user app, I'm just removing this PW. So I'm passing unsigned long ADDR, and I'm saying get the address of the kernel buffer and store it in ADDR. Okay, let's now try this. First, let's do our 64-bit, and it works. I got 1, 2, 3, 4, 5, 6, 7. Let's compile it for 32-bit. Now I have a 32-bit machine. It says inappropriate ioctl for device. So why do you think it's saying inappropriate ioctl for device? Can anyone guess? So can anyone guess like why it is saying, even if I have a compact ioctl, it is going into my ioctl, it is failing saying unknown command. Think what is the command number? How is the command number generated? Okay, I will make you more clear. So I'm running this user app, and you can see the messages. By this, you can easily tell what is changed. Sorry, I have to run. I'm running user app 1, which is 32-bit. Now let me compile it for 64-bit. Okay. Observe the change. There's a change in between running in 64-bit and 32-bit. Again, run it. Okay. I think it's now clear. It's very easy to tell why we are not able to. Why is this not working in 32-bit machine? Okay, let me make it more clear. So we know IOR, it accepts a magic number, it accepts a sequential number, and accepts a data type. And this is calculated, this command is calculated based on the size which you pass. So IOR command, this macro will calculate the size based on what you pass as a data type. So you can see in this code here, size is 8 in case of 64-bit, size is 4 in case of 32-bit, and the command has changed. Command has changed. Command number has changed. And as we don't have implementation for this command, in the switch case, it is saying unknown command. So how can I make it work? I can simply tweak it. So in the what I will do is, I will say, instead of using device ioctl, I will add my own compact ioctl, device underscore compact ioctl. And I will create my own command. So as I know, in case of 32-bit, it will be 4 bytes. I will create my own command number. And if someone is passing this command number, I will set it back to the actual command number. So this is what the actual command number, get across. So if someone is passing this command, this command, I'm converting it to the actual command. Now it will work. Now we have different ioctl functions for different bits. And now it worked in case of. So temporary command is same as what command we pass. And it has changed it to get address and it did work. Any questions till here? So let's cover one more example and then we'll stop the iOS video. So if I want to send a signal from my module to my from the module to the process, this function send underscore send. It accepts three arguments. First one is which signal to send, the PCD, the task struct of this particular signal. And third one is if I want to send it to a process or if I want to send it to a kernel thread. One is for thread, 0 is for processes. So this is the function if I want to send a signal to a particular task underscore struct. So what I have done in this is I have created three ioctl commands. First command will set the PID, so accept the PID. Second command will set the signal, which signal I want to send. The third command will send the signal. So third command will not accept any parameters. In the code, so everything is checking, error checking and validation. Set PID and get the PID from the user and then store it in a global value, set PID. And then I convert it into struct underscore task using PID underscore task. PID underscore task will convert it into task underscore struct. Given a PID, it will convert it into task underscore struct. User can also send set signal. This will set the signal which it wants to send. The default value of the signal is signal. The default value of PID is 0, null. And when I say send signal, if user has not called set PID before, I'm setting it to the current task struct and the current PID, and I'm calling send sig. 0 is as it is a user space process. So it's dev sig. In the user space app, I open a dev sig, I say send signal. So I'm asking it to perform the default action, which is sending it to this process and sending a sig pin. So let's run this code. So when you run this, so it is killed. Access OK return 1. We have not set the PID, so it is using current, and it has successfully killed. The next case, first I get my PID, calling get PID. I want to send a sig user 1. I also have a signal handler, a sig user 1. So we should use sig action, but I'm just for this example, I'm using signal. Signal handler is registered for sig user 1. I open dev sig, I set the PID, and I set the signal. So this is my PID and this is my signal. Now send the signal to this PID. I send this ioctl. And you can see it printed signal received, which is present in the code. It executed the signal handler. Let's revise what we have done till now. Try to answer this question.
Yes.
Unlock.
Unlock IOCTL.
All.
All the above.
Denotified.
Denotified.
No.
Access OK only will fail if I pass a kernel pointer to it. So I have not covered this. Okay. So we'll see this. So put user is faster than underscore yes. It is not faster.
Compact.
Combat IOCTL. Perfect. So we know put user and get user, and you can see what put user is doing here. Put user is first calling access OK. If it is successful, if access OK is successful, then it is calling underscore put user. Same case is being done by get user. Get user is also calling access OK first, then it is calling underscore get user. So if you are using access OK in your ioctl code, then you can directly use underscore put user underscore get user, and this will save you few cycles. This means it may be faster. This will be faster for you. So this is about like underscore put user and underscore get user. They are faster than put user and get user because they will not perform the access OK of this.